What are the applications of table constraints? Well, for some problems, it's quite natural to use the table constraint. And let's take, for instance, this puzzle that is called Eternity. It's an edge matching puzzle. So what you receive in input is pieces, square pieces like that. And as you can see, for each piece, we have a specific shape like this, okay, on each of the borders of the pieces. And the goal is to place on the board, so in that case it's a 4x4 board, to place all the pieces such that you have an equality between the edge matching shapes. Okay, you see that this is the constraint that we have. You've got an equality between all of them, like this. Okay, and the original puzzle is a 16x16 puzzle. And up to now, this puzzle is still not solved. Okay, so it's very, very hard. How do we model this puzzle in constraint programming? The model that I will introduce will use one variable for each side of the pieces. Okay, so this is the border. I will model it with the border. Okay, so this is a border. This will be the identifier of, okay, the identifier of the pieces. I assume that every piece is different and each has its own identifier. So this is the identifier of the pieces. And then I have a specific value to represent all the different types of borders that I might have, okay? So for instance, here I have given 0 for the gray shape. This shape is represented by number 4. This one has a number 0 and so on. Okay, and so I've got also one variable for each border here that I will put. And so what you can imagine is that depending on the piece that I will place, so let's assume that I will place this one here, then this would receive the value 4, this would receive the value 0, this would be equal 0, this would be equal 1, and this would be the identifier 0. Okay, and I will build the table because I don't know in advance where I will place each of the pieces, and also I don't know the rotation of them. Okay, it's totally fine if I have pieces that I would rotate it like this. Okay, it's also possible. And so I will consider a table that I will build that will contain tuples with 1, 2, 3, 4, 5 entries. The first entry of the tuple represents the ID. The second entry represents the identifier of the shape, which is up, right, down, and then left. Okay, so in that case, for this rotation, I would have 9. Up is 3, it's this one. Right is 3, down is 2, and left is 2. Okay, like this. And then I consider, of course, all the 4 possible rotations. And so I will have, this is the first one. Then I consider a second rotation, this is the second possible one, and so on. And I will do that for every piece that I receive in input. Okay, so I will create a big table like this. And how many tuples do I have? Well, I have in this case 16 pieces. Okay, 16 pieces multiplied by 4. And this is the length of my table. Okay, 16 pieces multiplied by 4 because I have 4 possible rotations for every piece. Okay. The domains of the variables, I forgot to mention that, but the domain of the variables is, because here I only have 4 different types of shapes. For the x variables would be from 1 to 4, and for the identifier it would be 1 to 16 because I have 16 different pieces. Okay, I also need to enforce that I'm not using 2 times the same piece. And for that, I will only post an all different constraint. You are already familiar with this constraint now. I will post an all different constraint on the array of identifier variables. So I take the I variables, each of them, I collect them inside an array, and I post an all different constraint. And this will make sure that I'm not reusing 2 times the same piece. Okay, And then to make sure that I'm not creating pieces out of nowhere, that I'm using the input pieces, I will use a table constraint like this. And I will say for every square I will post a table constraint. So for instance, for this square, I will collect the variable I33, which is there, x33, y34, x43, and y33. And I will make sure that this tuple belongs to the table. Okay, so this must correspond to one of the lines of the table.